If the numbers a sub n are defined by a sub 1 is 11 and a sub 2 is 21, and for n greater than or equal to 3, a sub n is 3 times a sub n minus 1 minus 2 times a sub n minus 2, we want to prove that a sub n is equal to 5 times 2 to the n plus 1 for all n greater than or equal to 1. Okay, so we're going to do this proof by the principle of complete induction. So we're going to do our base step first. Consider P of 1. So that's a sub 1 is equal to, by definition, 11. And we're going to show that it works for the formula as well. So a sub 1 is 5 times 2 to the 1 plus 1, which is 10 plus 1, which is 11. So it checks out. Let's go ahead and look at consider P of 2. So P of 2, we know a sub 2 is equal to 21. And for the formula, a sub 2 is equal to 5 times 2 squared plus 1. That's 5 times 4 plus 1, which is, of course, 21. So it works. Now let's consider P of 3 for the last one, just to show how the sequence is defined. So a sub 3, by definition of the sequence, is 3 times the preceding term, right? Minus 2 times the term before that, right? Now, this is equal to 3 times, so a sub 2 was 21, minus 2 times, and a sub 1 was 11. So this is equal to, so that's 63 minus 22, which is 41. Now we're going to check if the formula works for this term in the sequence, right? So a sub 3 by the formula is 5 times 2 cubed plus 1. So that's going to be 5 times 8 plus 1, which is, in fact, 41. So it looks like this formula works for how the sequence is defined. So we're going to show this, that it does work by induction, right? So induction, step. Suppose P of 1, P of 2, P of k minus 1, and P of k are all true. Okay, so I'm going to assume all these are true. In particular, I'm going to be looking at these two. So these two tell me that a sub k minus 1 is equal to 5 times 2 to the k minus 1 and plus 1. And a sub k is equal to 5 times 2 to the k plus 1. Now, assuming these, let's consider a sub k plus 1. By definition of the sequence, this is equal to 3 times the preceding term, which is a sub k, minus 2 times the term before that, which is a sub k minus 1. Now this is where our induction hypothesis comes in. This is equal to 3 times, so a sub k by the induction hypothesis is the same thing as 5 times 2 to the k plus 1 minus 2 times, and a sub k minus 1 is the same thing as 5 times 2 to the k minus 1 plus 1. And now let's see, this is going to be 15 times 2 to the k plus 3 minus 10 times 2 to the k minus 1 minus 2. Okay, so I'm going to have to get 2 to the k in both of these. So I have 15 times 2 to the k. 3 minus 2 is 1, so plus 1. And I'm going to rewrite this as 5 times 2 times 2 to the k minus 1, because 5 times 2 is, of course, 10. And 2 times 2 to the k minus 1, so 15 times 2 to the k minus 5 times 2 times 2 to the k minus 1 is 2 to the k, right? And now I have 15 2 to the k's minus 5 2 to the k. So that means I'm going to have 10 2 to the k's plus 1. And that is the same thing as 5 times 2 times 2 to the k plus 1. And 2 times 2 to the k is the same thing as 2 to the k plus 1 plus 1. So I was able to show that a sub k plus 1 is equal to 5 times 2 to the k plus 1 plus 1. And that's exactly what I wanted to show. Therefore, by principle of complete induction, for every n bigger than or equal to 1, I know that a sub n is equal to 5 times 2 to the n plus 1 for the given sequence, right? For the sequence that was given to us. Okay. And that is the proof.